Welcome to the Deep Dive. Today, we are opening up a rather extraordinary stack of developer logs and architectural notes provided specifically for you, our listener.
Yeah, and it is a massive stack of notes.
It really is. And to frame what we are about to explore, I want you to imagine, just for a second, that you are trying to build the ultimate, state-of-the-art, modern smart home.
Okay, I can picture that. Lots of touchscreens, voice control, that sort of thing.
Right. You have the latest AI, the absolute best environmental sensors, and basically infinite cloud computing power at your fingertips.
That's perfect.
It does. But for some bizarre reason, you are forcing this entire futuristic system to communicate exclusively through a mechanical 1940s rotary telephone switchboard.
Oh, wow. That's a choice.
Exactly. Every single time the AI wants to turn on the living room lights, it literally has to simulate a physical robotic arm, picking up a physical copper wire and plugging it into a physical brass socket.
I mean, it sounds like a beautifully complex form of self-sabotage.
Self-sabotage is exactly the phrase that came to my mind.
Because you are actively introducing an immense amount of friction into a system where modern software engineering has spent the last, 70 years trying to eliminate exactly that kind of friction.
It sounds completely absurd, but looking through the sources you provided for us today, this is exactly what a software ecosystem called Spirit is doing.
Yeah, and they're doing it with an incredible level of mathematical and historical precision, too.
Right. So our mission today is to unpack these developer logs chronologically. We're going to trace how this project starts as a relatively simple, elegant bridge for virtual machines.
And somehow evolves into this stunningly accurate, multi-layered emulation of the 1940s ENIAC computer.
Exactly. We're going to be talking about simulating literal vacuum tube failures, real-world voltage sags, and multi-axis data cartridges.
All designed to run advanced fluid dynamics and modern neural networks on top of simulated 1940s hardware.
Which is just wild to wrap my head around.
The philosophical reversal at the heart of these logs is what really makes this so compelling.
How so?
Well, usually we use modern software to abstract away the messy reality of physical hardware. I mean, we want our math to be perfectly insulated from the real world.
Right. You just want 2 plus 2 to equal 4. You don't want to think about the wires making it happen.
Exactly. But the developers behind Spirit decided to use perfect modern software to painstakingly recreate the messy, noisy, chaotic physical reality of the very first general-purpose electronic computer.
And they did it for a very specific strategic reason, which we will get to later.
Yes, definitely a massive payoff for all this effort.
But let's build this from the ground up, because before the developers even approached the ENIAC emulation, they had to lay down the absolute ground rules for the entire Spirit architecture.
Right, the absolute basics.
And the foundational building block of this whole ecosystem is something they call the Spirit medium.
A medium, in the context of this software architecture, is essentially a typed container.
Like a sandbox.
Yeah, you can think of it as a specialized, domain-specific environment. The architecture relies on several of them to separate different tasks.
So they aren't just throwing everything into one big digital bucket.
No, not at all. They have a core medium that handles central logic, an abstract syntax tree medium, a GL medium for graphics rendering, an event bus medium for routing messages, a scheduler, and a linker.
That is a lot of different mediums.
It is, but it's a highly modular way to break down a massive computing environment so that no single part is overwhelmed by the complexity of the others.
Let's pause on a few of those terms for a listener who might not live inside a code base every day.
Good idea.
Like an abstract syntax tree, or AST, is basically a way of mapping out code like a sentence diagram.
Oh, that's a good analogy.
Thanks. Instead of reading code line by line like a book, an AST breaks it down into a tree of logical operations.
Yeah.
Like this verb modifies this noun, this function triggers this variable.
Right, gives the code a strict structural hierarchy.
Exactly. And then the GL medium, the graphics layer, that's where the visual heavy lifting happens. The logs mentioned dealing with float 32 arrays and compiled shader code there.
Which sounds intimidating, but
Yeah, float 32 just means a decimal number with a floating decimal point that takes up exactly 32 bits of computer memory.
yeah.
It's just a standard for highly precise graphical math.
Right, and that separation of duties is standard practice in software.
But Spirit does something weird with it, right?
Very
Right.
weird. The defining characteristic of the Spirit ecosystem, the cardinal rule that governs every single one of these mediums, is what the developers call the decimal surface rule.
The decimal surface rule.
Yeah, and this is a striking architectural choice. The rule dictates that the outside interchange format, the only way these different mediums are allowed to talk to the rest of the system, is strictly decimal. Base 10.
Wait, so not binary logic?
Nope. Not binary, not hexadecimal code, just pure decimal.
So if the Spirit virtual machine wants to tell the graphics medium to clear the screen, it does not send a complex binary packet full of zeros and ones.
Exactly. It sends a simple decimal opcode, like the number 100, and perhaps a few decimal arguments.
Everything on the outside surface of a medium is just a number you or I could read off a piece of paper. To make this relatable for the listener, I was reading these logs and picturing the front of house versus the back of house at a really chaotic high-end restaurant.
Okay, I like where this is going.
So the customer, which in this case is the Spirit virtual machine, sits in the quiet dining room. They look at a menu with numbers. They tell the waiter, "I'll have item number 100.
Right.
That is the decimal surface. The customer doesn't need to know, and frankly shouldn't care, what is happening back in the kitchen to make item 100 appear.
The restaurant analogy perfectly captures the concept of architectural encapsulation, because inside the kitchen, inside the Spirit medium itself, the data representation can be absolutely anything.
So they aren't forced to use decimal inside the medium.
Oh, no. The developers gave themselves total freedom behind closed doors.
Gotcha.
The graphics medium kitchen might be wrestling with those complex float 32 arrays, shifting massive buffers of memory directly on the computer's graphics card, and compiling raw shader code.
And the abstract syntax tree kitchen might be juggling deeply nested JSON objects or complex symbolic math expressions.
Exactly. But the waiter only ever carries the base 10 number 100 through the swinging doors into the dining room.
So if I'm looking at this from a high-level systems design perspective, what is the tangible benefit of imposing this incredibly strict decimal border control?
I mean, why not just let the virtual machine speak the native binary language of the graphics card?
Yeah, wouldn't that be faster?
It creates an incredibly robust, almost indestructible encapsulation boundary. Because the virtual machine only ever sees decimal opcodes and decimal arguments, the VM itself remains remarkably simple and lightweight.
Oh, I see. Doesn't have to know how to render a shadow.
Right. It never gets bogged down in the specifics of rendering graphics or parsing trees. The linker, the part of the software that connects all these different mediums together also remains simple because it only has to track decimal node IDs and simple dependency edges.
It also provides unparalleled human readability.
That is a huge part of it, yes.
Because if a developer is debugging the system, they aren't staring at a massive hex dump. You know, a wall of letters and numbers trying to decipher memory addresses.
Right. Which is usually a nightmare.
Instead, they're looking at a clean, structured list of base 10 numbers. It is stable, it's easily inspectable, and it forces a kind of rigid discipline on the entire architecture.
The interface is just a number, regardless of whether the kitchen is using a modern microwave or a wood-fired oven.
And once the developers established this universal, simplified language for the front of house, they realized they could use that total freedom in the back of house to simulate something incredibly difficult.
An architectural paradigm that is completely alien to modern computing.
Which brings us to the 1940s EONIs.
Yes. We are moving from the theoretical architecture into a masterclass in historical emulation.
The EONI was completed in 1945. And for context, it did not use bytecodes.
Right. It didn't have a modern central processing unit or a CPU that reads lines of text and executes them.
It didn't even use binary, right?
No, it didn't. The ENIAC was a decimal machine, and you operated it by literally walking around a room the size of a small gymnasium, plugging thick black cables into sockets, and manually turning physical dials.
The developer logs show this realization dawning on the team. They realized that if they wanted to truly emulate the ENIAC inside their newly created ENIAC medium, they couldn't fake the underlying mechanics.
They couldn't just write a modern software function that says add variable A to variable B and then put a vintage sepia tone filter over the user interface.
Yeah, that would be cheating.
Exactly. There is a specific quote from the logs that summarizes this philosophy. Hard to be ENIAC if you don't function with ENIAC in ENIAC format.
Meaning no fake pulses allowed.
None. To achieve true historical and architectural fidelity, they decided to emulate the ENIAC's physical mode of operation.
So they had to build a virtual pulse generator.
Yes, a real software pulse generator that runs at a specific frequency, say 1,000 hertz.
Wow.
It meant building 20 distinct 20-digit decimal accumulators. And an accumulator isn't just a memory slot.
Right, it's not just holding a number.
No, it's a piece of hardware that handles math by physically stepping through digits via electrical pulses.
They also built function tables, which in the real world acted as 1,200 individual 10-way mechanical switches used to look up values.
And perhaps most daunting, they built an explicit physical plug board in the software.
Okay, let's slow down and explain how a physical accumulator actually works, because it helps explain the madness of this software.
It is definitely madness.
On the real ENIS, an accumulator used ring counters.
Right.
So imagine 10 vacuum tubes arranged in a circle representing the digits 0 through 9. If the tube representing 7 is glowing, meaning it holds an electrical charge and the machine wants to add 1, a physical electrical pulse is sent down a wire.
A literal burst of electricity.
Yes. That pulse hits the circle, turns off the 7 tube, and turns on the 8 tube.
And the Spirit developers replicated that exact discrete pulse-driven reality in code.
Which is it's staggering to think about.
Every single instruction in this ENIAC medium must be physically mapped. If you want to perform a simple addition, a pulse fires from the generator.
Okay.
That pulse must be logically routed through a specific plug on the virtual plug board. It travels down a simulated wire to a function table row, which reads the physical position of a virtual switch.
Let's say it reads a 5.
Right, so that value of 5 is then sent as a sequence of 5 distinct pulses down another wire to an accumulator, which physically ticks its virtual vacuum tubes upward 5 times based on those incoming pulses.
Okay, I am really struggling to wrap my modern developer brain around this.
It's a lot, I know.
Because if I want a computer to add 5 and 5 today, I just use a plus sign in my code.
Right, and it takes a microscopic fraction of a nanosecond.
Exactly. Writing a software program to simulate a literal physical cable connecting to a simulated brass port, to route a simulated electrical pulse, to physically tick a simulated vacuum tube dial, just to add 2 single-digit numbers together.
The computational overhead must be staggering.
Why introduce that level of inefficiency? It feels like they're just showing off.
It seems highly inefficient until you look at the broader architectural goals outlined in the logs.
Okay, what were the goals?
First, they are proving the ultimate flexibility of their decimal surface rule.
Oh, right. The waiter at the restaurant.
Exactly. They are demonstrating that their front-of-house waiter can perfectly encapsulate a computing paradigm that is physically alien to the modern machine running it.
So they're proving that the kitchen can literally be a 1940s room full of tubes, and the waiter still just brings out the number 100.
Exactly. But more critically, it is about capturing temporal reality.
Temporal reality, meaning how long it physically took the electricity to move through the machine in 1945.
Yes, exactly. When you emulate the physical routing of pulses, you aren't just making sure the final math is correct, you are capturing the exact timing of how the math was achieved.
Because the distance the pulse travels matters.
Yes. The ENIAC's word list developed by the team reflects this reality. You don't see simple add or subtract commands in their logs.
So what do you see?
You see physical routing commands. Things like PBP lug to physically connect 2 units on the plug board, or FT lookup to read a mechanical switch.
They are programming by routing virtual electricity.
They really are.
But a computer, even an incredibly accurate simulation of a 1940s computer, is totally useless without a program to run on it.
Right, you need instructions.
And in 1945, saving a program meant leaving the cables plugged into the wall and not letting anyone touch them.
Which is not exactly practical for a modern software environment.
No. So how does the Spirit ecosystem store a massive physical configuration of cables and dial settings in modern software?
This challenge led to the creation of what is arguably the most sophisticated architectural element of the entire ecosystem, the Spirit cartridge.
The cartridge. When I first saw the word cartridge in the source material, my mind immediately went to blowing the dust out of an old Nintendo game.
Oh, yeah, the classic plastic brick.
Right. You have a plastic brick with a little ROM chip inside, and its only job is to hold the game code.
It just sits there and feeds data to the console.
Exactly. But the deeper I read into the logs, the more I realize that analogy falls completely flat.
Yeah, the Nintendo analogy is far too simple for what's going on here. The developers explicitly describe the Spirit cartridge as a multi-axis, multi-medium container.
Multi-axis.
It isn't just a static script or a single file of code. It is a unified vessel that holds 6 distinct representations, which they call axes, of the exact same conceptual object.
It's less like a Nintendo cartridge and more like a combination of a Russian nesting doll, a physical blueprint, and a translator.
That's a much better way to describe it.
Let's walk through these 6 axes because understanding this structure is key to understanding how the whole system operates.
Okay, let's break them down.
Axis 1 is the Spirit Card program. This is the domain-specific language, or DSL.
The DSL is the high-level, human-readable code. It describes the intended behavior of the program in a way a modern developer can understand and write.
So that's the easy part. But Axis 2 is the ENIAC microcode. This is where we drop down to the hardware layer.
Right, it gets real very fast.
This axis is the actual data structure, defining the physical 1940s wiring schematic.
It maps out the plug board pathways, the conditional pulse gates, and the literal switch positions required to execute the behavior defined in Axis 1.
It translates the human intent into the physical reality of the ENIAC.
Exactly. Then we have Axis 3, the compiled bytecode.
What does that do?
That is the heavily optimized set of instructions that the Spirit virtual machine actually executes under the hood to make the simulation run efficiently.
Okay, so Axis 1 is human code, Axis 2 is 1940s wires, Axis 3 is modern machine code.
You've got it. But Axis 4 introduces a completely different computational paradigm.
Oh boy.
Axis 4 is the neural network medium formative data.
The cartridge contains its own machine learning brain.
Yes, it doesn't just hold code, it holds neural embeddings, learned network weights, and formative training data specific to whatever math problem the cartridge is trying to solve.
So the cartridge has the capacity to adapt and learn on its own.
Exactly. It's a living thing, in a way.
Then Axis 5 is the cartridge buffer, and we will explore the rules of that buffer momentarily because they are fascinating, fundamentally changes how the system processes information.
Definitely. We'll need to circle back to that buffer.
And finally, Axis 6 is XML serialization.
This is the formatting layer that ensures this incredibly complex, multi-layered beast can be saved to a hard drive, inspected by a human, and shared across different systems without losing any of its internal logic.
So to recap the nesting doll, the cartridge holds the human intent, the physical blueprint of the 1940s circuitry required to realize that intent, the modern bytecode to run the simulation, a neural network brain learning from the process, a private memory space, and a file format to save it all.
It is a highly autonomous, self-contained computational universe.
The autonomy is the critical feature here, and it is entirely governed by Axis 5, the cartridge buffer.
Right, the gatekeeper.
The developer logs outline incredibly strict rules for how this buffer operates.
The primary rule is that local state is authoritative per cartridge.
What does that mean in plain English?
It means the cartridge has its own private scratchpad memory, and this scratchpad is purely internal. It is never, under any circumstances, exported or seen by the rest of the Spirit ecosystem.
And when you consider the architecture we just discussed, that rule makes perfect sense.
Oh, absolutely.
Because if you were simulating a 1,000 hertz pulse generator, routing thousands of virtual electrical signals through hundreds of virtual plugs, and ticking vacuum tubes up and down dozens of times a second.
The sheer volume of data being generated is astronomical.
Right. If all of that raw, messy, intermediate data was broadcast to the core software network, the entire system would drown in its own noise.
It would crash immediately. The private buffer allows the cartridge to think locally.
The EIAC emulation is churning through thousands of pulses, making intermediate mathematical calculations, and the neural network is simultaneously pondering its embeddings, all behind closed doors.
The rest of the Spirit software is completely blind to this internal struggle.
They have no idea it's happened.
Nope. The integration to the wider core network is strictly gated by a single vital function called process buffer.
Going back to our restaurant analogy, the front of house only ever sees the final plated dish.
Right, the waiter just brings out the steak.
They don't see the chef dropping a pan, burning a sauce, or adjusting the seasoning.
Only when the cartridge has finished a meaningful routine, say, completing one full clean step of a massive physics simulation, does process buffer take the final normalized decimal values and push them out into the Spirit medium.
It is the ultimate realization of the decimal surface rule, but applied to time and state computation rather than just formatting.
The cartridge perfectly encapsulates the chaos of the physical emulation.
Okay, so we've established the hardware, the ENIAC medium, with its painstaking pulse routing and plug boards.
Orlin, we have established the software container, the Spirit cartridge, with its multi-axis brain and completely private buffer.
Right. The burning question for anyone reading these logs is, what do you actually do with a machine like this?
Yeah, what's the point of building this whole thing?
What kind of data did the developers feed into this meticulously crafted simulator?
Instead of giving it a modern coding test, they went straight for the historical heavy hitters.
They wanted to push it to its limits.
Exactly. They fed it the exact life or death math the real ENIAC was built to solve during and immediately after World War II.
The logs detail the creation of two highly specific mathematical payloads, the ballistics cartridge and the flow cartridge.
Let's start with the ballistics cartridge. This is the foundational purpose of the original ENIAC calculating the trajectory of an artillery shell through the air.
And the mathematical approach detailed in the logs is integrating time-marching ordinary differential equations, or ODEs.
Right, for a listener who hasn't taken a calculus class recently, an ODE is an equation that contains one or more functions of one independent variable and its derivatives.
In time-marching.
Time marching means the ENIAC is not calculating the entire parabolic arc of the artillery shell in one sweeping mathematical stroke.
So it's not just drawing a curve on a graph.
No, it is freezing time, step by step.
Okay, so it calculates the exact position of the shell at millisecond 1, factors in the current velocity, applies the drag of the wind to the pull of gravity, moves the shell forward a tiny fraction of an inch.
And then it completely recalculates all those variables from millisecond 2.
Wow.
Precisely. And the logs show exactly how the developers assigned the physical 20-digit accumulators for this specific task.
They mapped the math directly to the hardware.
Yes. Accumulator 0 holds the position of the shell on the x-axis. Accumulator 1 holds the y-axis position.
Accumulator 2 tracks the velocity on the x-axis, and accumulator 3 tracks the velocity on the y-axis.
Right. Accumulator 4 holds the acceleration variables, accounting for that aerodynamic drag. And accumulator 6 acts as the master clock, tracking the tiny time steps.
It is a deeply visceral way to think about math, because as we discussed, these aren't just abstract memory addresses in a modern RAM stick.
They're physical unit.
Right. To update accumulator 0 to move the shell forward on the x-axis, a virtual pulse has to fire, route through a plug board into a virtual multiplier unit, physically multiply the velocity sitting in accumulator 2 by the time step in accumulator 6, and then route the resulting pulses back into accumulator 0 to physically tick the vacuum tubes upward.
They are performing calculus using simulated mechanical relays.
It's incredible. The ballistics cartridge is an incredible feat of engineering. But the second cartridge, the flow cartridge, operates on an entirely different level of mathematical complexity.
Oh, absolutely. We are moving from the trajectory of a single artillery shell to the behavior of supersonic fluid dynamics.
The flow cartridge is designed to solve for the steady, supersonic flow of a perfect gas around a physical body.
And the specific shape mentioned in the logs is a cone cylinder.
So imagine a bullet or a rocket punching through the atmosphere faster than the speed of sound.
Instead of time-marching ODEs, the math requires space-marching partial differential equations, or PDEs.
Space marching. How is that different from the time marching we just talked about?
Right, so instead of calculating point A to point B over a sequence of time, we are calculating the pressure, density, and velocity of the air across a fixed spatial grid as the supersonic object disrupts it.
So you're looking at the whole area at once.
Yes. The machine is solving a brutal, interconnected system of equations.
The logs list them out. They have the continuity equation, which is a mathematical way of ensuring that mass is conserved.
Because air doesn't just magically disappear when a rocket hits it, it gets compressed and pushed aside.
They have the Euler momentum equation, detailing how the forces balance out. And they have the energy equation, which the developers define as q squared plus a squared equals 1.
In that equation, Q represents the velocity of the gas, and R represents the local speed of sound.
And all of this has to account for the chaotic rotation of the airflow caused by the curved shock wave that attaches to the front of the cone cylinder.
And again, they are executing this brutal math without a modern CPU.
Right, they're using the function tables.
They are utilizing the ENIAC's function tables, those physical banks of 1,200 10-way switches, to literally encode the complex gas relations and shockwave physics.
So if the machine needs to know the speed of sound for a specific localized pressure point, a pulse routes to a switch position to look up that exact value.
Exactly. It is a continuous pulse-driven sequence of finite differences.
I want to focus on that term, finite differences. Because when you replace continuous smooth calculus derivatives with discrete finite difference quotients plotted on a grid, you inevitably introduce error.
Yes, you're essentially pixelating reality.
Pixelating reality, that is an excellent way to conceptualize it.
If you take a high-resolution photograph of a smooth curve and zoom in far enough, the curve becomes a jagged staircase of square pixels.
Right.
If your spatial grid for the fluid dynamics simulation is too chunky, your physics simulation becomes blocky and inaccurate. The larger the distance between your grid points, the more physical reality you miss in the gaps.
Which brings us to a profound mathematical strategy detailed in the logs, a technique designed to solve this pixelated reality problem.
The developers implemented something called Richardson extrapolation.
And the source material references the historical work of mathematicians like Frankel, Alexieva, and Gorsat, who focused heavily on finding the absolute error limits in complex flow fields.
Richardson extrapolation is a brilliant mathematical workaround for finite computing power.
Because you can't just run an infinite grid, right?
Exactly. Instead of trying to run one impossibly fine microscopic grid, which would take the ENIAC centuries to compute the system, runs the exact same supersonic flow problem multiple times at different, relatively coarse grid sizes.
So instead of one massive simulation, they run a chunky simulation, a medium simulation, and a slightly finer simulation.
The logs specify running the problem where the grid spacing, represented by the variable h, equals 18. Then they run it again at 116 and again at 132.
Okay, so you have these three different runs, then what?
Once those three simulations are complete, the system isolates specific points in physical space that are common to all three grids.
It looked at the computed values for velocity, density, and pressure at those specific coordinates.
Right. By plotting those three different values against their respective grid sizes, the math allows them to fit a curve to the data.
You look at the trend line of the chunky, medium, and fine grids, and you mathematically follow the arrow down to 0.
You extrapolate backwards to see what the value would be if the grid size hires approached an infinitely small, perfectly smooth 0.
You find the true reality hidden in the pixelated data without having to actually compute the infinite grid.
It's brilliant. And the visualizer, the GL1 graphics medium we discussed earlier, is responsible for interpreting all of this.
Right, at the front of house.
It doesn't just plot static dots representing pressure. It reads the derivatives, the physical rates of change calculated by the ENIAC accumulators across these grid points.
The logs refer to these as hyperplane gradients.
By reading these mathematical rates of change, the user interface can dynamically render the curvature of the supersonic shockwave.
It renders the Mach contours, mapping the speed of the airflow and the trajectory vectors in real time.
It takes this archaic, pulse-driven math and translates it into a stunning visual representation of physics.
At this point in the architecture, we have a beautifully orchestrated system.
Really do.
We have a robust medium architecture, a flawless ENIAC emulation, and Richardson extrapolation, providing theoretically perfect mathematical limits. The math is soaring.
But then the developers hit a wall.
And it is not a wall of code or processing power. It is a historical and philosophical wall.
Because the physical reality of the ENIAC was that it was never perfect.
This is where my understanding of modern software development experienced a hard reset.
It's jarring, isn't it?
Totally. As a software engineer, your entire mandate is to eliminate bugs, to ensure that memory is stable, and to guarantee that a mathematical operation is flawless. 2 plus 2 must always equal 4. But these developers intentionally pivot. They explicitly separate the ideal math from the physical reality.
The developer logs state this philosophy plainly. Spirit can be perfect, but ENIAC, by design, is finite, noisy, and lossy.
The realization is that if you simulate perfect math on a perfect, frictionless virtual machine, you are no longer simulating the ENIAC.
You are just wearing its clothes while cheating at the math.
Exactly. So the cartridges, the ballistics and flow cartridges, contain the ideal perfect equations.
But the Spirit ENIAC VM itself, the environment executing those equations, is intentionally coded to inject historical, physical imperfections.
They literally spent time writing code to generate hardware noise.
It is a masterstroke of historical modeling. They identified and explicitly coded the specific types of physical degradation the real machine suffered.
Let's break down the noise sources they modeled because there are quite a few.
First, you have voltage rail noise. The real ENIAC ran on a nominal 150-volt power supply.
Okay, 150 volts.
But when a mathematical operation requires firing thousands of vacuum tubes simultaneously across the gymnasium, the electrical grid sags under the immense physical load.
The power flickers.
Exactly. The voltage drops. The Spirit virtual machine mathematically models these transient voltage drops and spikes in real time.
Which means the master clock, the 1000 hertz pulse generator, is no longer a perfect metronome.
That leads directly to pulse noise. Because the voltage is fluctuating, the electrical pulses driving the entire machine suffer from timing jitter.
A pulse might arrive a microsecond late.
Yes. And sometimes, because of a voltage sag, a pulse is physically too weak to trigger the next vacuum tube in the sequence.
So what happens then?
The result is a misfire. An instruction is simply skipped.
Wow.
Inversely, sometimes a tube double fires, executing a single addition instruction twice.
So you could be right in the middle of calculating a critical space marching step for a supersonic shockwave, and the machine just arbitrarily decides to skip an addition step because a virtual vacuum tube didn't receive enough virtual voltage.
Yes, that is absolute chaos.
And the physical modeling goes even deeper than that.
They modeled tube reliability. Vacuum tubes are analog components. They drift in their gain, they suffer from intermittent, unpredictable failures, and they have warm-up instabilities where they don't function correctly until they reach a certain temperature.
And on top of the physical component failure, you have the arithmetic imperfections inherent to the machine's design.
The logs were very specific about the arithmetic limitations. Because the ENIAC only possessed 20-digit accumulators, the engineers programming it had to constantly shift numbers to the right to avoid overflowing the physical capacity of the machine.
Right, because if a calculated number grows too large, it spills over the top of the accumulator and completely breaks the calculation.
So to preserve the calculation, you shift the entire decimal number down, but every single time you shift a decimal number to the right, you physically lose the least significant digits.
They just fall off the edge of the accumulator into nothingness.
Furthermore, the ENIAC hardware for multiplication and division was only guaranteed accurate to about 9 decimal places.
So practically speaking, what does this actually mean for the final result? When the flow cartridge finishes churning through thousands of noisy pulses and spits out a final pressure value for the cone cylinder, how wrong is it?
To understand the impact, the developers draw a crucial distinction between truncation errors and round-off errors.
Okay, let's untangle those.
Truncation error is what we discussed earlier regarding the grid size, the mathematical error caused by pixelating the physical space.
And Richardson extrapolation is designed specifically to fix truncation error.
Right, but round-off error is entirely different. Round-off error is the hardware noise. It is the lost decimal digits, the voltage sags, and the misfiring pulses.
And Richardson extrapolation, no matter how elegant the math, cannot fix a misfiring vacuum tube.
It cannot. The logs state that because of these cumulative hardware realities, even if the ENIAC simulation outputs a glorious 10-figure number, only about 6 of those figures possess any actual mathematically significant truth.
Wait, so the bottom 4 digits?
The bottom 4 digits are essentially just a pile of accumulated electrical noise.
That is wild.
The entire architecture has to respect that historical ceiling. It cannot pretend to have 10 digits of pristine mathematical precision when the physical reality of the 1940s only guarantees 6.
Okay, I have to stop and wrestle with this concept.
Go for it.
I completely understand the novelty of it from a historical preservation standpoint. It is a fantastic academic trick to make your modern simulator suffer exactly like the real 1940s machines suffered.
It is a great trick.
But functionally, practically, why would any developer voluntarily build a broken computer?
Wow.
If the ultimate goal is to know where the artillery shell lands or how the supersonic gas behaves, why would you let a simulated voltage drop actively ruin your math?
It is the most vital question of the entire project. Why voluntarily introduce chaos into a perfect system?
Exactly. Why do it?
The answer is that the noise is not broken, the noise is honest. Yes, we live in a physical universe, and computation, fundamentally, is a physical process governed by thermodynamics and electrical resistance. If you want to deeply study how error propagates through complex systems, you desperately need that noise.
Okay, I see.
But the true genius of the Spirit project is revealed when you look back at Axis 4 of the cartridge. The neural network.
Right, the AI brain sitting inside the cartridge learning as the simulation runs.
Yes. In modern computer science, if you train a neural network purely on perfect, frictionless, mathematically ideal models, that network becomes incredibly brittle.
Because it expects the real world to be perfect, too.
Exactly. The moment you take that AI out of the laboratory and deploy it in the real world, perhaps on an edge device in a remote location struggling with a fluctuating battery, or in the future on a quantum computer constantly battling atomic decoherence, The AI fails catastrophically because it has never experienced physical noise.
So by intentionally subjecting the perfect mathematical models to brutal physical constraints, the Spirit developers are creating a hyper-realistic adversarial training ground for modern AI.
They aren't just playing dress-up with vintage technology. They are systematically using the mechanical flaws of the past to harden and prepare the artificial intelligence of the future.
The ENIAEs isn't just a calculator here. It is an obstacle course for the neural network.
Which perfectly sets up the final, crowning architectural achievement detailed in these developer logs. The unified pipeline.
The unified pipeline, that's where it all comes together.
It is where every single disparate piece we have discussed, the decimal surface rule, the physical hardware emulation, the multi-axis cartridges, the complex differential equations, and the intentional injection of hardware noise, all violently snap together into a single cohesive process.
The developers refer to this final implementation as stacking cartridges over a shared hardware buffer.
Let's trace a piece of data through this stacked pipeline step by step because the choreography is a thing of beauty.
Let's do it. We start at the bottom of the stack with the physics, right?
Yes, the ballistics cartridge or the flow cartridge is doing the heavy lifting, grinding through the ODEs or PDEs.
But crucially, it is running inside the noisy Spirit ENIAS VM.
It is suffering.
It is suffering immensely.
Well,
And as the physics cartridge runs, it writes its intermediate mathematical state into the shared buffer.
but this shared buffer has a highly specific hardware axis attached to it.
What does that axis do?
This axis does nothing but track the exact physical telemetry and metadata of the virtual machine in real time. It creates a ledger of suffering.
A ledger of suffering.
It records things like, at millisecond 42, pulse 45 dropped. The master voltage rail sagged to 142 volts. Accumulator 3 shifted right and lost a significant figure to round off error.
So side by side in the buffer, you have the math representing the artillery shell and a meticulous ledger of every single physical mistake the machine made while trying to calculate that math.
Exactly. The next layer up in the stack is the gradient error cartridge.
Okay, so that's where the Richardson extrapolation comes in.
Yes. It takes those raw, noisy mathematical outputs, looks at the different chunky grid sizes we discussed, and performs the Richardson extrapolation to find the theoretical limits of the physics.
But it is performing this high-level math on data that it knows is physically compromised.
And then the entire package, the math, the extrapolation, and the ledger of mistakes, is handed up to the neural network cartridge.
This is the crescendo of the architecture. The neural network axis does not just look at the final trajectory of the artillery shell and try to memorize the curve.
No, it ingests the mathematical trajectory and the hardware noise metadata simultaneously.
So over thousands of runs, the neural network learns to correlate specific physical hardware events with the resulting mathematical drift.
The AI looks at the data and realizes, okay, every single time the main voltage rail drops below 145 volts, the virtual multiplication unit drifts by a tiny predictable fraction, which ultimately causes the artillery shell calculation to fall 6 meters short of the target.
It is learning the machine's specific personality. It is learning the physical fingerprint of the errors.
It is an astonishing application of machine learning. The neural network isn't just learning aerodynamics or ballistics, it is learning active hardware compensation.
It learns to predict the necessary mathematical corrections for the coarse grid solutions based entirely on the physical noise it observed during the calculation process.
It acts as a highly adaptive, intelligent filter, mathematically smoothing over the historical imperfections of the virtual vacuum tubes in real time.
And finally, all of this enriched, corrected data flows to the very top of the stack, the GL1 visualizer cartridge.
The front of house.
Exactly. When you look at the screen, the interface doesn't just show a simple dot representing where the artillery shell impacted.
It outputs the pure math and the messy physics side by side.
You see the extrapolated impact distance, but you also see a live readout saying pulse reliability, 98.2% fired, 1.1% dropped. Average voltage fluctuation, 7.3 volts.
You are watching a 1940s machine physically struggle to comprehend the universe, and you are watching a 2020s AI seamlessly catching it every time it falls.
It is a profound architectural synthesis. The Spirit developers have managed to build an ecosystem where the abstract, mathematically ideal intent of the software is cleanly, surgically separated from the messy physical reality of the hardware.
Allowing both layers to be independently studied, visualized, and learned from simultaneously.
It is a phenomenal journey through these logs. I mean, we started with the spirit medium and the strict decimal surface rule.
An interface that mandated simplicity at the borders while allowing total chaotic freedom behind the scenes.
We watched as the developers used that freedom not to build a sterile modern computer, but to obsessively physically rebuild the ENIAC.
Committing to the temporal reality of 1000 hertz pulses, 20-digit ring counter accumulators, and virtual plug boards.
And we explored the sheer density of the Spirit cartridge, a 6-axis container acting like a Russian nesting doll.
Housing human code, physical wiring blueprints, neural networks, and a tightly controlled internal buffer that allowed the massive ENIAC emulation to think locally without drowning the larger system in raw data.
We saw that system tackle the grueling, space-marching math of supersonic fluid dynamics, utilizing Richardson extrapolation to hunt for the smooth truth hidden inside chunky, coarse grids.
We confronted the philosophical pivot of intentionally injecting historical hardware noise, voltage sags, pulse misfires, and truncation errors into a perfect mathematical space.
Culminating in that towering stacked pipeline where a modern neural network constantly observes the chaos of the vacuum tubes, learns the intricate patterns of their physical failure, and dynamically corrects the output.
It's a masterclass in software architecture and historical preservation.
It really is. But, tracing the flow of perfect math through noisy hardware and watching an AI learn to compensate for the physical exhaustion of the system, it leaves you with a really provocative thought, not about computers, but about us.
Oh, how do you mean?
Well, we spent all this time in modern engineering trying to build perfect math boxes, right? Trying to hide the noise of the physical universe from our software.
Yeah, that's the whole goal usually.
And we tend to think of our own human brains the exact same way. We treat our minds like perfect logical engines that are supposed to calculate flawless decisions.
But the reality is our brains run on incredibly messy, noisy biological hardware.
Exactly. A sugar crash is basically a voltage sag. A lack of sleep is a pulse misfire.
Hormones introduce constant truncation errors into our logic.
We are running complex algorithms on constantly degrading biological hardware.
That's a fascinating way to look at it.
Right. And maybe what we call human intuition, that gut feeling that corrects our logic when we can't quite articulate why, isn't magic.
Maybe human intuition is actually just our own biological neural network doing exactly what the spirit AI is doing.
Exactly. Running a constant subconscious Richardson extrapolation over the messy physical noise of our own bodies, learning the fingerprint of our own biological errors, and seamlessly catching us when we fall.
That is, wow. That's a really incredible thought to end on.
Thanks. I think it gives us all something to mull over. Thank you to our listener for joining us on this deep dive, and we'll catch you next time.